All right, I think we're ready to go. So thank you for who's on here. The goal of this presentation is just to provide some very basic understandings of radio direction finding. This will be recorded, so if anyone wants to look at it before the actual event, then that's the goal of this. So the title of this presentation is Basic Radio Direction Finding Techniques. This is actually a modified / expanded version of a presentation that I gave at the QSY Society meeting. I believe it was back in April of this year. So we're going to hit on 5 major things as part of the presentation. Top 4 common methods for radio direction finding. I'll abbreviate that as RDF for brevity. And then I'll talk about some options of how you can participate in an event like this, or just do radio direction finding from home, from mobile, from foot, and then helpful items to have right now. So the top 4 common methods for RDF, there's a lot of acronyms in here, so please bear with me. So A of A stands for arrival of angle. I'll also refer to that as peak and null. Then we have heat mapping. Both of these are considered the easiest ways to do any type of radio direction finding. And then something a little bit more complicated, but it depends on how you think of what's complicated, is time difference of arrival, or TDOA. And then finally, we have pseudo Doppler, and also that's not only a little bit more complex, it's also a little bit more expensive, and I'll get into that a little bit later. So first, let's look at angle of arrival. If you look at the upper right of the corner, I made a little grid. So this is the least expensive and the least complex way to have some fun doing radio direction finding. Most common antenna is something that needs to be directional. And this photo right here is a simple Yagi style antenna. The best thing that you're going to need to figure out is how to understand how your radio and your antenna work together for peak and null. And so if we look at this, this chart next to the antenna, the front of the antenna is known as the maximum lobe or forward gain. So that's what's typically is used to find the peak of a signal because it has the most gain from an antenna. But then if we look at other parts of the antenna pattern, so for example, the radio that popped up on the screen, we can see that the signal meter is at full scale. But what happens if you're nearby a signal? There's some other tricky ways that you could utilize an antenna like a Yagi antenna by using what's called the null. So if we look towards the side of the antenna, or even towards the back, you have a null. And so aiming your antenna counterintuitively away from the signal, if you're familiar with how your antenna particularly works, you can get a very accurate reading. So 2 different options there, peak and null. And again, this really comes down to how you can utilize the equipment that you have. Now, if we look at expanding this angle of arrival, what happens when we start to add mapping? So if you're aiming an antenna in a particular direction and you're getting readings for strongest or weakest, you can start to plot that on a map. So let's say, for example, if you take signal measurements from multiple points, you can combine them on a paper or a tablet computer to see where the signals intersect, like that. So there's a couple ways you can go about this. You can either physically take yourself and your antenna and your radio, and you can move from location to location. And if you're really familiar with where you are on your map, if you were to move, let's say, 500 feet in one direction to the other, you can line up your own bearings and see where they intersect on a map. The photo that we see at right is Bob QAK's finger from a past fox hunt. And he used a similar method by switching his locations. But there's also another way that you can go about this. Let's say, for example, if a few of you were trying to find a signal and you had a way that you can accurately communicate the bearing of what you're receiving, if you were all at different locations, you could actually get this done a lot quicker. But coordination of that is actually pretty hard. So you have to have like a really good plan with who's in your little team of, how would you actually go about this? But again, taking angle of arrival and overlaying what you're discovering on a map could really give you some great directional and fairly accurate ideas as to where a signal is coming from. Then it gets harder when you get closer to it, which I'll get into. But again, this is what is called angle of arrival plus mapping. And again, you can do this on foot. You can do this from home. You can do it in a car, not while you're driving is what I would suggest. But again, this is the least expensive way of doing RDF. If we get into the next more expensive and slightly more complex is what's called TDOA, or time difference of arrival. Why I say that this is a little bit more expensive is because equipment tends to be a little bit more specialized, so you will be spending more for something like this compared to a Yagi antenna, which you could use for other purposes like actual communications. A TDOA antenna is only going to be used for something like RDF. And even though it's technically not really more complex, the way that it's designed is actually more complex compared to an AOA Yagi type of an antenna. So the way that these particular systems work, there is a circuit that basically rapidly switches between the signal that's received and the actual math. You can see there at the right, nobody's going to be able to figure this out in real time, right? So that's why we're letting some electronics that are built into these TDOA type of antenna systems do all the heavy lifting. So it's basically just flip-flopping within nano or milliseconds between each of them, and then it outputs that in a way that humans can figure out which way the signal is coming from. So you let the antenna really do the hard work, and then as a human, basically most TDOAs will either output its results either in some type of an audible or visual way. So for example, the antenna pictured, when you have that connected to a radio, when the signal is received at both antennas at the exact same time, you hear nothing else in the receiver. If they're slightly out of phase, meaning one antenna might be even just a fraction different distance from the transmitter, you'll hear a tone come through your radio. And so if you just hold the antenna the correct way, if you don't hear a tone, you know that the antenna is aimed directly at the source of the transmitter. But that's only in a perfect world. The way that these TDOA type of antennas work, at least the simple type, is you don't necessarily know if it's coming from the front or the back of you. So that presents a little bit of a challenge. But if we take TDOA and we combine it with a map, again, if you move to different locations, you could probably get a feel for how this basically works. So if you're not hearing a tone and you're moving, let's say, 500 feet in a straight line, and if you slightly have to modify the angle of how you're holding a TDOA antenna, you'll get a pretty accurate fix. And again, plotting this all on a map really makes a lot of sense, because then you can see what you're doing, and then you can figure out where the actual signal is coming from. And again, that works great if you're just on your own. Trying to coordinate this with people, I think, is a novel approach, but again, takes a little bit of coordination, clear communication with who's in your team, things like that. So this one I really like, heat mapping, and you'd think, well, wow, why is this both like the least expensive and kind of more complex at the same time? Everyone has different skills, and this is something that requires a little bit of some computer knowledge. So you're blending RF and computer stuff. So basically what heat mapping does is it takes signal measurements from multiple points in real time, and it combines them with GPS location. So as you move your receiver system, that's what's capturing this. And that's why I say this is a little bit more complex. I wouldn't say that you want to really be walking around the woods with a computer and the system. Can you do it in the car? Absolutely. That's a lot better. The link that I have there is the application, or one of the applications that you can do heat mapping with. So you can take a look at that, and this is what that visual output would look like. So say if you had a heat mapping system in your car and you were driving around, basically as you gather more points, this is basically what it will look like. So on that map where the area is red, that's where the signal is strongest, and that's basically where the signal was coming from. So some of the things that you can get into this relatively inexpensively, outside of just needing a computer that can run the necessary application, you can get by with using an inexpensive SDR dongle, radio receiver. The one pictured is the RTL-SDR version 3. They have a 4 version out. These run $30, $40 a piece. You can do lots of other things aside from heat mapping or radio direction finding and stuff. So you might already have one of these. So you could put this into use for that. You would also need a USB GPS. Those sell for about $10 US. And so basically, as you're receiving things, even with like a little magnetic mount antenna that you could also pick up off of Amazon for a couple dollars, all in as shown, excluding your computer, you're maybe only spending about $50, $60 in total. And combining all of this gives you the heat map. Again, it's a little slower. It's not best for short signals. So if there's something that's maybe transmitting once every 10 or 15 seconds, this would be harder to do heat mapping with. But think about other signals, that you can benefit. So maybe some locations compared to others. Maybe if you were driving around, you can see, well, why is the signal stronger in one particular area or another? This might even give you some other ideas of maybe optimizing your home ham radio station to see where your signal might be stronger, or maybe a repeater or something like that. But really, heat mapping, I find, is probably best for like broadcast signals, or maybe over time. To do this for radio direction fox hunting, I wouldn't really suggest this. But if you were driving around anyway and you were capturing signals, it might be fun to look at that over time. But again, this is a common RDF method, but maybe not best for doing fox hunt. But again, this is another option that's available. And like I said, it's very inexpensive. So now we get to the last one before we dive into some of the more specifics. This is called pseudodoppler, or correlative interferometry. Boy, that's quite a tongue twister, and you can see that it's more expensive and it's more complex. And so basically, this takes a lot of all the other techniques that we've already covered. It improves on what we learned about under TDOA, uses the basic same theory, but instead of flipping and flopping between two antenna elements, you're going to end up using 4 or more. So if you look at that graphic over at right, through the magic of electronics, it basically electronically samples, in this case, 4 antennas, and it outputs that in a way that we can find what's the direction. Once you go from 4 to 5 antennas, the accuracy increases. And there's some other options out there that include even more antennas. And so if we look at that graphic all the way at bottom right, that's an array that's used in the 800, 900 megahertz range. I'll let you all count the antennas, but it's a lot more than 4 and a lot more than 5. But basically, the more antennas that you have, the more complex the system is. But what it allows you to do is sensing through all of the antennas through a common device allows you to do some pretty neat things. So the screen grab that I have here is a device called a Kraken. It's probably the best device out there today that's not really super duper expensive. In the past, there were some other systems called a Doppler, a company named Ramsey Electronics, which is for the most part gone out of business. They were a main provider of those to the amateur radio and related community. Today, if you were looking at something like this Kraken device, all in between antennas and the box itself, I think it's about $700 or $800. So it's kind of affordable recreational, but maybe not really for everybody. And again, so this is more expensive. But the cool thing that this offers is it outputs everything to a map on your cell phone, and then it even gives you driving directions to where the signal is. So you only need to drive around for a little while, and it just figures it out. It's pretty amazing. So that's what's the difference within correlative or pseudo-Doppler. Again, more expensive if you're really getting into fox hunting or doing stuff maybe professionally or whatnot. This is kind of like the top of the end. Again, I wouldn't say go out and spend this money right out of the gate. See if you like doing fox hunting, you could always level up to something like this. So switching tracks here, if you wanted to do radio direction finding from home, this is not necessarily just for this upcoming event. So if you want to do radio direction finding from home, what are some things that you need? Well, first, you're going to need a directional antenna, which you can rotate. Next thing you're going to need is a low loss way to connect the antenna to a radio. Now, chances are if you have, let's say, a 2-meter Yagi at home, or even a directional HF antenna, you already have everything you need. There's nothing that you need to do any different. Maybe the radio that you have, hopefully it has some type of a signal meter. So as you move the antenna, you can see where the signal is strongest or weakest. Again, same thing like learned before, having some way to plot these. So if you're at home, having a paper map or even some type of electronic mapping, if you know which way your antenna is rotated, basically you just want to output that. And you can do this all from home. Now imagine if you had 5 or 6 friends with similar type of setups, you can easily find the location of a signal very accurately. And that's the real key. The ability to be accurate is super duper important. Now I'm not going to go through every little bit and piece on here. Again, that's why we're recording this. But this just kind of walks you through a common workflow. So if you're going to rotate your antenna, you want to take a bearing at maximum signal. You want to kind of understand how your antenna works, where you start to lose and gain signal. This is known as the beam width of the antenna. So some antennas have a narrower beam width, which are probably more helpful for this compared to something that has a wider beam width, because then you don't necessarily know where it's strongest because the degrees of accuracy are less. But basically, you know, if you're working with a few others, you could probably narrow it down pretty well. If you do have a home setup and the signal is particularly strong, you might have an attenuator. You might have that as a function on your radio known as RF gain, or you might have some type of an outboard device. But again, that's something that could help you determine the direction and the strength of a signal. And recording all of that information is really important. So blowing that out to a map, here we have Bob's finger, but in super high def. And so let's imagine if there were 3 home stations represented by locations A, B, and C. They aimed their antennas. They all seemed to get the strong signal. Everything came into this direction. Then let's say they maybe relay that information to somebody on foot and say, hey, chances are the signal is somewhere near the top end of this little pond at Ferncliff Forest, and somebody can just walk over there and see if they can find the transmitter. So there's lots of ways that maybe even folks from home can assist those that maybe are on foot or even mobile. And this is known as trilateration. So you can technically do this with 2 stations. 3 is better. If you have more, it gets even more accurate and faster to find a fix where a signal could be coming from. So now if we look at radio direction finding from a mobile viewpoint, same things apply. Antenna with directional properties, chances are you're not driving around on a day-to-day basis with a Yagi antenna on your car. I would not advise that, but just because you're mobile doesn't mean that you can't have an antenna like that. Pull over, take a bearing, move to another location, etc. So something with an antenna with directional properties is really important. Also having an attenuator for strong signals. And so chances are if you're in a mobile and you have some type of a directional antenna, maybe if you get too close to a signal, you're going to need to figure out a way to attenuate that. And there's some devices that I'll cover a little bit later. Sometimes you have a function like that on a radio in the car, like a mobile, but many of them do not. So you might need an outboard type of a device. So I'll give you some other tips in a moment. Of course, you're going to need a radio with a decent signal meter. And because you're mobile, chances are you're going to get close to it. So I would suggest having a handheld or some other gear that you can use when you get nearby the signal when you hop out of the car. And most importantly, which I cannot stress enough, the ability to be safe and accurate. Teamwork really helps here. So if you're driving around, don't be fiddling with knobs. Have a passenger do that. Or if you're hopping out, you know, just multiple hands make short work. So most importantly, be safe. I don't want to hear anybody driving around and, you know, crash or create an issue. So always be safe. I think everyone's probably a safe driver, but just want to stress that you don't want to have additional distractions while driving. So a lot of the same things that I've covered from home really can drive down into the mobile side. Some other tips here beyond talking about attenuation. You can also tune off the frequency of what you're hearing, even by just a few kilohertz. So if the signal gets stronger and you tuned off, that might give you a little bit better idea as to how close or which direction it is. There's also another mechanism called harmonic monitoring. So if you have a capable radio, the way that electronics are fashioned, you have harmonics. This also, kind of relates to the musical world. So let's say if you took a frequency like 146.565 megahertz and you multiply it by 3, it puts you at 439.695. If you had a radio capable of tuning to that second frequency, you're most likely going to hear the signal, but at a reduced level. And so that's really helpful when you get very close. If it's a very powerful signal, we may be talking about 1,000 feet. If it's somewhat weak, a lot closer. So that's a real helpful tip. You could also go fifth harmonic, but I don't think many people have radios that will tune up to 900 megahertz or even greater than that, depending on what you're monitoring. Other tips that I had mentioned, be aware of your surroundings. Signals will reflect off of things like mountains and buildings, and water towers and trees and rocks and fences and all sorts of things. So if you think that you got a good reading from when you were doing your normal mobile, if you hop out and you're getting some kind of a strange reading from another location, look around. You might be getting a reflection off of something. And so that's why it's helpful to keep track of what signal levels you are getting from different locations using your directional antennas and, see what you're kind of putting together. And again, just wrapping up on the mobile side, safety. Do not drive a vehicle while you're doing stuff like this. Please pull off on the side of the road. Just, safety first. And speaking of safety, you can see some mobile installations, some old, some more modern, with some crazy antenna contraptions. But notice 2 of the 4 pictures are stationary. Looks like the guy with the Yagi antenna on the white car. You have a passenger and a driver. So a little strange, but those are directional antennas. And then the picture at the bottom left, that's using a Doppler type of setup. So you only have some short little pointy antennas instead of something else. And so that's kind of what the difference of these would look like. And then if we drop into by foot, and again, you notice there's a lot of similarities here, so I'm not going to kind of just go through every little bit and piece here. But if you're on foot, and I think the audience on here has done a number of different on-foot fox hunts, so don't add adapters. If you have an antenna that's directional, that's handheld, and you have a radio, try to go as direct of a coaxial connection. Don't add antenna adapters. Every little thing that you do that allows signal to leak into your antenna will throw off your directional bearings and readings on your radio. If you have a graduated signal meter, that's really important. You want to be able to figure out how strong the signal is or not. Some of the cheaper, inexpensive radios may just say signal or no signal. So that's not really too helpful for this. Again, great way to brush up on some of your map and compass skills. We've already talked about attenuation. And then another device that you might want to grab, I'll go through this a little bit in more detail on a later slide, a field strength meter. When you get really close, there are some other devices out there that can help you figure out when you're really close. And if you didn't even want to have a piece of equipment, if we look at the big grid there, one of my favorite things is what's called the body fade method. So when you're very close, and this is really best for like an in-person demonstration, if you take your radio with a rubber duck antenna, your body will actually attenuate the signal. So if you're facing away from the signal, using your body as the in-between, if you notice that you have a signal fade, chances are the signal is in the opposite direction. And so it's really hard to kind of explain some of these techniques, through a presentation like this. And that's why, having some in-person training and people pairing up with others who've done this or want to experiment is really great. So again, these slides will be shared, and then also same thing with this recording if everyone wants to maybe print these out or, save it on your phone or whatever. So what will you need for doing radio direction finding from foot? Directional antenna, low loss way to connect your radio with a graduated signal meter, paper and electronic mapping, and ability to be accurate. So I think that's all kind of drilled in pretty well by now. And helpful items to have right now. If you wanted to just get a start in radio direction finding, what will you need? So first thing, which is also a nice little fun project, You could do a Google on this, a VHF tape measure Yagi, or you could also look into a UHF tape measure Yagi. So these are easy to construct. There's me holding two VHF Yagis made out of some tape measures and PVC. There's a 3-element one, which has higher gain, but I've found that for most on foot fox hunts, the 2-element one, which is designed similar but different, has proven to work extremely well. So inexpensive projects. You could also use these for transmitting, so it's not just for radio direction finding. You could find some other uses for these. And the size for those two are for the 2-meter VHF band. If you had a UHF version, think of it as being like 2.5 times smaller. And so using that harmonic theory, you can use a UHF Yagi antenna to find VHF signals. It's going to attenuate the signal, but it still gives you the same directional properties. And so if anyone's looking for an additional project, if you already have a VHF one, try making a UHF one and see what works best for you. We've already talked about handheld radios. And when I say a good signal meter, well, this is an out of production radio. I just felt like it was a good example. There's many other radios out there, and I'm not going to endorse any specific model. But one that has like a graduated signal meter. So if you look under the frequency, you can see that it has multiple segments. And so that's what's really good. Shortest way to connect the antennas and stuff together. We already covered that. A small clipboard's helpful. You can hold a map. Also, if you have a small ruler and a pencil. And then some other devices, again, I'm not going to get into, something like a nano spectrum analyzer. You can hook an antenna up to this, and it works as a really great RDF tool or a field strength meter. And then finally, we talked about attenuators. You have a big heavy duty one over at right, or there's another device called an offset attenuator that you can look into by Googling that. But these are some items that I would suggest if you're new or if you're looking for some new things to add to your list of things for RDF. That's what we have. And with that, again, the goal of this was to really only cover things related to RDF, not really drill into the specifics of the event because we have a very informational and clear flyer. But I think we're coming up on time. I'm happy to take some